So far, we've talked about materials that are perfect, at least chemically, uh, and the structure for the most part as well. We did talk about amorphous materials that don't have much of a structure, that are random, but we want to get into defects. Defects plays a huge role in all things about materials. So to start off, there's no such thing as a perfect crystal or a material free from imperfection. There are 4 dimensions of defects that we're going to talk about. 0-dimensional are called point defects, 1-dimensional are line defects, 2-dimensional are interfacial defects, and 3-dimensional are bulk defects. Within these, there's 2 other types of defects or imperfections, and those are ones that are chemical. That would deal with the composition, the element, the atoms that are used, the molecules that are involved, and there are those that are structural, talking about the atomic arrangement or the microstructure. So we're going to go back to this picture again. We have the composition of the atoms is important, and that's for a material in general, along with the atomic arrangement. But these also play a huge role in defects as well, not just the material in general, but also in the defects of the material. We have to talk about the composition of the defect. We have to talk about the arrangement of the defect. And again, all these things really come back to energy. The defects, whether they're chemical or structural, will change the energy of the material, which will change how the material properties work. And that's why we really care about them, because the energy changes everything about the material. A lot of times when you think about defects, you think, oh, those must be bad. But defects aren't always bad. So the more we understand about defects and how it changes the energy of the material, the more we can actually add imperfections or defects on purpose. And this gives us specific tailored properties. Again, that comes back up to this picture about our what we really want. We want very specific things out of it. When we design any type of product, or when we design a material, we want things to be very, very, very specific. An example of this, and I know that we haven't gone into it yet, so you might be unsure about some of these things that we'll be discussing in this example, but you can always go back to this and think about it once we have discussed it. An example would be a 0-dimensional chemical defect. A good version of that would be something that's alloyed or doped. We do this on purpose. We alloy metals. I can have a metal and sprinkle in a little bit of some other atom, a different type of metal, and it's going to change the properties. It'll change everything from the melting point to its strength to its electrical properties. It changes everything. An impurity, that is when we say that it's bad. We try not to do this. We try not to do it on purpose. And depending on the material, there might be a level of impurity that might be okay to have up to a certain point. But again, when you're talking about so many different atoms throughout an entire material, you're going to have some type of imperfection. You try not to. They're not on purpose, but you're always going to have some. All right, so let's actually talk about what some of these things are. So the first thing we're going to talk about is point defects. Point defects are 0-dimensional. They are thought of as a point. They're localized disruption on a regular lattice, or it sits between lattice sites. And I'll draw a couple pictures of that in just a minute. I did want to very quickly talk about some notation. When you talk about a 0-dimensional point defect, what you do is you write out the defect atom, and then you, as a subscript, you write where this is on the lattice, and then as a superscript, you write whether there's some type of charge difference involved. So let's talk about substitutional first. A substitutional, it means that this is going to occupy a normal lattice site. It's not like we're adding anything in here. It's going to sit on a normal lattice site. This would be our dopant or an alloy, or in the case of our example above, an impurity, a contaminant. And so I have a couple things here for the dopant. We might have phosphorus into silicon, an alloy might be magnesium into aluminum, or a contaminant might be lithium into sodium. All right, so the example that I'm going to show here, I'm actually going to draw one. We're going to have aluminum, and the aluminum I'm going to draw just as an empty circle, and copper I'm going to draw as a filled circle. And so if I have an aluminum lattice, this is a pure crystal. But if I were to substitute any one of these aluminums and put a copper in instead, this material would still be aluminum. It's mainly aluminum. It does have a contaminant or an alloy or something in there. There's something in there that's not supposed to be for a pure aluminum lattice. And so what we would say is that a copper is sitting on an aluminum site with a neutral net charge. So again, if we're talking about the notation here, we have our copper atom. That is the main thing that we're writing here. The subscript is where it's at. It's at an aluminum site. And there is no change in charge because a copper atom is neutrally charged and an aluminum atom is neutrally charged. So there is no charge difference. So that's substitutional. Strictly just we replace one for the other. We have what's called an interstitial. This occupies a position between lattice sites. Again, we could think of this as an alloy, such as carbon in iron, or a contaminant. You could also have what's called a self-interstitial, where, which I'll show a picture of in just a second. So let's say that my iron are these large open ones, and carbon's actually a little smaller. So I'm just going to put a dot onto that one. And so here is my iron, and this would be all pure iron. But what I could do is I could put a carbon atom in here. And carbon's so much smaller than iron that we can't just move out one of these irons and put a carbon in its place. Instead, these carbons are small enough that they can actually sit between lattice sites. And so in this case, carbon is sitting on an interstitial site. Interstitial in between. It's not an actual lattice site. Carbon is sitting on an interstitial site with a neutral net charge. Again, carbon isn't charged, iron isn't charged, and so just because we add a carbon, we don't have more electrons than protons at this point, so we're still at a net charge. So carbon is sitting at an interstitial, no charge that has changed there. Lastly, we have a vacancy. This is when we have an unoccupied lattice site. So here is my gold. And if this is supposed to be a perfect crystal, I would just have these circles all the way throughout, but we're missing one. There's a spot here in the middle where I could put one, where one should be if this were a perfect crystal, but there isn't one. So this is a vacancy. So what we would write that a vacancy is sitting on a gold site. It should be gold, and there is no charge. So these are our three type of point defects. Substitutional, we just substitute. Interstitial, we have something sitting not on a lattice site. And we have a vacancy. There should be something, but there isn't. And so here's our picture. We'll look at these bottom three first. We have our interstitial. We have this spot in between, this little green spot down here at the bottom left, a smaller atom in between lattice sites. We have this large red atom off to the lower right-hand side. Substitutional, we have something different where a blue atom should be. In the middle, we have our vacancy. There should be a blue atom there, but there's not. And up here towards the top, we have our self-interstitial. It's still a blue atom, but we've wedged an extra one in here, and so it's not necessarily sitting on a perfect lattice site. And it might be hard to see, but if we try to draw a line through any one of these directions, I could draw a line this direction, which works out. But if I try to draw one up this way, we see that these aren't necessarily lining up. There's some stuff there that are not in the proper spot. And so we have some stuff not sitting on a lattice site. That would be a interstitial, and because it is the same atom as the rest of the lattice, it is a self-interstitial. They're pretty simple in metals. If we're talking about ionic materials or ceramics, they're a little bit different. We're going to just go through this really quickly. I'm not even going to discuss the notation necessarily. You can look at this notation. We have the same type of things. We have the Schottky. That's a double vacancy, and the reason we need a double vacancy is because we need a neutral material, and since ionic materials are made up of charges, I would have to have equal charges missing on both sides. So in this case, a +2 and a -2 both need to be missing so that the material is still neutral. So double vacancies, the vacancies come in pairs. We have the Frankel. These are interstitial. Same idea. We again need to make sure that we have a neutral atom by the time that we're done with this though. And so we can have an interstitial, but we'll need a vacancy somewhere else or something to make up for the fact that we've put some extra charge in the material. We have to take some charge out somewhere else. And then we have what's called F-center. And F-center is going to be when we have positive and negatives, right? Because that's what we always have when we make up. So positive, positive. Every other one is a positive, and this is how a material, an ionic material, gets made, which means I have my negative ions here. I should have a negative ion in this spot, but I don't, let's say. To make sure that we still have a neutral atom, instead of having a negative ion here, I could just have an extra electron. It's sitting there. The material is still neutrally charged, which is what we need for it to be stable. But our negative charge is coming from an electron rather than a negatively charged ion. So here are a couple pictures here. I have the Schottky. I have the plus charge here, and I have the minus charge here. But as long as I have a plus-minus pair together, then everything's okay. Again, I have a Frankel where I have a missing and a two missing ones, two vacancies, but one is a negative and one is a positive, which means that, again, I have neutral charge. And so for ceramics, it's a little bit different. I know I went over ceramics quickly. We're not going to talk about ceramics as much, but I did want to introduce it. So if ceramics interest you, you're going to probably, there was some extra stuff here, just about how we have to make sure that we have neutral pairs to maintain charge balance. If you are interested in ceramics, at least there was something here. You can look back and do a little bit of studying on it yourself with a quick picture of what's going on. The one that we're actually going to probably spend the most time on is talking about line defects, and these are one-dimensional. There are two types, and I know I have three things here. The first one is called an edge dislocation. The second one is a screw dislocation. The third one is just a mix. It means that we could have both of them. So it's not necessarily a third type. It just means that we could have both of these in the same material. And so the question here is what, and we'll get to what dislocations are in just a minute, but the overarching question is, what do dislocations do within a material? I want you to have that in the back of your mind while we describe what the line defects, these dislocations, are. First off, I do want to say that there are theoretical strength of materials, such as a yield strength, versus what we actually measure for that strength. Is about 10 times difference. And so our actually measured our measured strength is 10 times less than what we thought the theoretical strength should be. And we could, theoretically figure out how strong a material is, because a material is just as strong as all of its bonds. And so we could sum up all the strength of the bonds. We get a number. What we're actually getting when we take a measurement is about 10 times less than that. So it's very interesting. And it has to do with edge dislocation. So that's kind of why I wanted to just put this out there while we talk about what a dislocation is. All right, so an edge dislocation is simply just an extra half plane of atoms within a crystal. Here's my crystal. This is a perfect crystal. It's a 4x4, everything's nice, everything's sitting at a lattice point. If I put an extra half a plane somewhere in here, I have to kind of move some things over to fit this in here. I would wedge them up into here. I'm going to go ahead and change the color real quick. I would put some atoms here, and I say it's a half a plane. Remember that this material is coming in and out of the screen. And so I have this plane of atoms that I put in here, and I say that it's only half a plane because it doesn't go all the way through the material. Up here, we don't add that extra part of the plane of atoms in here. We don't wedge that in there. We have a notation where I kind of put this capital T where this extra half plane of atoms is at, where the bottom part of our T points towards that new plane of atoms. What we can do is we can find this dislocation, and we use what's called a Burger's vector. And it describes the character of our dislocation, in this case, our edge dislocation. So what I'm going to do is I have my lattice here, and if I start at one point, let's say that I start here, if it's a perfect structure, a perfect crystal, I should be able to draw a circuit and start or end wherever I start. So if I go up 4, to the right 4, down 4, and to the left 4, I should finish at the spot that I started. So let's go ahead and do that. I go up 1, 2, 3. I don't have enough, so I'll actually just go up and over 3. 1, 2, 3, 1, 2, 3, and then back 1, 2, 3, and I start and stop at the same point. That shows me that I have a perfect crystal. If I do the exact same thing here, I'm going to start and I'm going to go up 3, 1, 2, 3, over 3, 1, 2, 3, down 3, 1, 2, 3, and then over 3 again, 1, 2, 3. We see that I don't start and stop at the same point. There's a gap somewhere, and the reason there's a gap is because we have a dislocation. If I were to then draw a vector from where I started to where I stopped, some people draw it the other way around as well. Some people are sticklers about it. I say, again, because the orientation of the crystal doesn't matter, I could have drawn my circuit in the opposite direction. The important part is I have a vector. In this case, it's going right to left or left to right. This is my Burger's vector. We write that with a B and put our little vector sign above it. And that's a Burger's vector. And really all it's doing is it's telling us what's going on within our material, where our dislocation's at. And it tells us that our dislocation is somewhere that encompasses this circuit that we drew. So we can do it a couple more times. I have some lattices that I've written out here. We're going to draw a circuit. We've got to make sure that we have the same number of units in each direction. And if it's a perfect crystal, there is no Burger's vector. And if there is a dislocation, then our beginning and end should not line up. So up 1, 2, 3, 1, 2, 3. I could do up 4, I could do up 5 and over 4 and 5. It really doesn't matter as long as I'm consistent. So again, I start and stop at the same spot. In this case, up 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. We have our Burgers vector right here. All right, so for an edge dislocation, remember there's a couple types of dislocations. This one is an edge dislocation. The Burgers vector is perpendicular to the dislocation. So the dislocation is right here. Remember, I can write it with this capital T, where the bottom part of this T is pointing to this extra bit of planes that I've wedged in there. My Burgers vector is going left to right. And here I say that the Burgers vector is perpendicular to the dislocation. The dislocation is a line, and this line is coming in and out of the screen. This kind of looks like I just have this point where this is happening, or you could say the line is this extra plane of atoms that I've kind of circled in here, but really the dislocation is the line that comes in and out of the screen. It's just at this very top part right here. And it goes into the screen and it comes out of the screen, and just that very top atom right there, where that dislocation, where this T is pointing to it, that is the line. And so we can see that if I have this line coming in and out of the screen and I have a Burgers vector that's going left to right, those are perpendicular to each other. There are going to be some stress fields in this crystal. And the idea here is, let me go ahead and I'm actually going to take this circuit away really quick. I have some spots here where I've wedged in an extra plane, which means these ones on the bottom here, these are going to have to be compressed a bit, right? Because I'm wedging more stuff into a smaller space. I kind of have it spaced out so that it's easy to see, but I did wedge in an extra set of atoms here, an extra plane of atoms, which means those are going to be compressed. And if those are compressed, these ones are going to try to be pulled apart. So these ones are in tension. So some that are trying to be pushed, they're being compressed. The other ones are kind of being pulled apart a little bit. And then we have the ones on the side here. And here we have our shear. These ones are kind of being pulled at an angle. And so it is important, and we'll get into this a little bit more when we talk about mechanical properties, and we talk about things being in compression or tension or shear. But it is something that I just want to note here. Inside of this, anytime I have a dislocation, the side with an extra plane is in compression. The side without the extra plane is in tension. And on the left and the right, we have shear stresses. And so altogether, we have compression, we have tension, and two shear fields within just this simple small portion of our lattice. Now, going back to this original question that I asked way up here about why our material's strength isn't what we thought that it would be. In theory, we don't see that when it's measured. Comes down to the fact that this dislocation has the ability to move. And it moves so that the material deforms, or it's how the material deforms, and it's why this strength isn't theoretical. This dislocation, instead of the material having to rip apart all at once, this dislocation allows it to move one row at a time. It means that we have to break fewer bonds at a time. So let's say that I have a lattice like this, and I have this extra plane of atoms kind of on this left-hand side, and I give this a push. So I kind of give it this shear push. I push on the bottom in one direction, I push on the top in the other direction. What I'm going to do is I'm going to push this closer. This is going to get pushed in a little bit, and what I have to do is I can break the bonds right here at the very, very beginning. Just one set of bonds. I don't have to break all the bonds all at once. And when I do that, my material does this. And if I keep pushing, it's going to keep moving through the material, and eventually it will end up on the other side. I have some better pictures down at the bottom, so we'll be able to talk a little bit more about how this moves. But what it's really doing is it's just moving one step at a time. When I push this over, one bond breaks, or a line of bonds breaks. Right here, it reattaches where that broke, so this new spot reattaches, and then it just does it again. We keep breaking one set of bonds and pushing over, one step at a time. So I do have a summary for the edge dislocation, and this again will take time to think about. The direction of motion is going to be parallel to my Berger's vector. And so let's go back up to this picture here. All right, so we can look at it here as well, look at things move. If I were to push this, I could push this so that it bonds here, which means that this is no longer attached, but as I keep pushing it, it will attach, and it will slowly push things over until this is no longer attached and it's kind of sitting off by itself. So there it is, kind of from our lattice perspective. And the reason I wanted to show this one is, remember that I had my Berger's vector that went right to left. So there's my Berger's vector. So the direction of my dislocation, my movement, is parallel to my Berger's vector. The direction of motion is perpendicular to the edge dislocation, and the direction of motion is in the direction of the applied shear stress. So I apply my shear stress, I push this material together, and that is the exact same motion of my edge dislocation. So the edge dislocation direction parallel to the Berger's vector, perpendicular to the edge dislocation, and in the same direction of the stress that I apply it in. All right, screw dislocation. It's not an extra half plane. Instead, it's that the lattice is sheared. Part of the lattice is offset. And so we're still going to draw a circuit, but the circuit's never going to meet up. It's going to spiral. Now this one's much, much harder to draw. I'm going to try drawing it a couple times, then I'm going to show you an actual something from a book so that it's a little bit better. Now let's say that I look at a plane of atoms, and I'm looking directly down on it, and they all go in this direction. And this is my lattice site. So I have these dots here, and everything lines up because this is a perfect crystal. Now that is one plane, and materials are made up of multiple planes of atoms. So I put another plane of atoms on top of here, but for some reason, the plane shifts. And so that means that it shifts all the way down. That's what a screw dislocation looks like, and it's hard to see. So I have a stack here, and everything was going fine. Everything was just going left to right, and then all of a sudden I have a plane that that has this little squiggle in it. It doesn't match up perfectly. Now I'm going to try one more, and I apologize if it ends up not working well, but I felt like I should at least give it a shot. All right. This is my material. So those are my edges. Let me see if maybe adding a second color will help here. This is my three-dimensional material. And so here on the bottom, I just have a stack of cubes. And the stack of cubes should be perfect. What I have on the top here is I'm going to have another stack of cubes. But at some point, this stack of cubes kind of shifts over a little bit. So that it looks like it's almost starting to unzip. A lot of times I even refer to this as a material is unzipping slightly. So the dislocation is right here. It's going to be the spot kind of where the zipper's at, as if I were to pull this zipper, let's say, up this way, it would pull this line over to here, and it would pull this line over to here, and I'd have a perfect stack of these cubes. Like I said, I will show some better pictures here in just a moment. In this, all stress fields are going to be considered shear. There are no compression, there's no tension, everything is shear. I mentioned that this is kind of like a zipper. If I zip this up, then this top set of atoms, this top three-dimensional stack of boxes, since I kind of do this lattice, will shift over. But if I were to zip this down the other way, then these stack of boxes on the top, this lattice, would shift over one. And so if I were to unzip this, I'll go ahead and draw it down here. If I were to unzip this, by the time I'm done, I would end up with something that looks, hopefully, something like this. So if I were to zip it up, it would look like a perfect stack of boxes. If I were to unzip it, the whole thing would shift over. Another picture, I'm going to try one more picture again. Hopefully one of these pictures at least ends up working out well. So I have this, I have kind of this offset box on the top, and this looks like this. And as I apply some type of force this way, it is going to unzip or it's going to zip depending. And either push everything out so that I have an entire stack of lattice sites that are now open, or it's going to stack right on top of it so that everything looks perfect. Move quickly through that. I do have a summary for screw dislocation. The direction of motion is going to be parallel to the Burger's vector. I'm going to draw the Burger's vector for this in a second. I don't want to do it on one of my drawings because my drawings aren't very good here. The Burger's vector is parallel to the dislocation, and the direction of the dislocation is perpendicular to the applied shear stress. All right, so I have this picture here. And if I apply a shear stress, first let's review the edge dislocation. If I were to push this over and push the bottom one the other way, I'm going to draw an upside down T here for my dislocation, because again, that bottom part of my T points that extra set of atoms, and that's the extra set of atoms is pointing up. I draw my circuit around it. I end up with a Burger's vector. That's my edge dislocation, and as I move this, this moves to the left. This top part does. My screw dislocation's over here on the right. We can see that it's kind of unzipping. We kind of have this spot where it's not lined up and then it lines up perfectly. We would do the same thing. We would start at a given spot and we would go down. In this case, we go down 5, I believe. 1, 2, 3, 4, 5. Then we're going to come forward. 1, 2, 3, 4, 5. And then we're going to go up 5. 1, 2. Well, we're off plane now. We don't necessarily have a plane of atoms there. So I actually have to go in the plane, into my material a little bit so that I can finish going up. 2, 3, 4, 5, and then 1, 2, 3, 4, 5. And so again, to complete my circuit, there's this stair step here. And that's why we call this a screw dislocation. As I make this circuit, I kind of have this spiral. It kind of looks like the threads of a screw that kind of spiral either in or out of a material. And so I get my Berger's vector, which is actually a stair step at this point. It's actually in 3 dimensions rather than just the 2-dimensional picture that we have for our edge dislocation. Here is a little picture of our edge dislocation. So I have a perfect looking crystal here, but I apply some force. And on this side, I apply a force going the other way. And as I do that, I break bonds. I end up with this extra set of planes. And as I continue to push it, eventually it offsets the entire thing, and I get this picture at the end. The screw dislocation is when instead of doing it and moving the whole top over one step at a time, I'm only going to move part of it. So I just kind of move the front portion at a time, but I move the entire front, right? Not just one length and then kind of have this compression in here. Instead, I just kind of pick up this whole front end and I shift the whole front over. And then I take the next line back and keep moving that over until I've unzipped the entire material. The deformation at the end basically looks the same. It's just the matter in which it happens. All right, next we have interfacial defects. These are our 2-dimensional defects. These are interfaces, free surfaces, and internal surfaces. All right, so a free surface, what we're looking at is that the number of bonds of the atoms is less than inside the bulk material, and less bonds, bonds that would like to be made but aren't, makes it a higher energy state. That isn't necessarily the best explanation, so let me go ahead and draw a quick picture. Here is my lattice. And again, if this is a perfect crystal, this continues in all directions. But let's say that I have a free surface, just a surface like the surface of your table or something. These all want to bond together. But the ones on, and these ones, remember, it keeps continuing into the material and to the right and to the left. But the ones on the top, there are unmet bonds here. They want to bond to something, right? It wants those extra bonds, but there's nothing there for it to bond to. That's what we mean by a free surface. This is the same thing that happens with interfaces or internal surfaces. Anytime things match up, but they don't quite bond all the way. And this is why it's high energy. It's seeking for that bond, but it's never quite getting that. High energy means that it's more reactive. On some reasons, that's good. We can use this for catalysts. But for other things, it's bad. It means that things are going to be more corrosive. Again, interfaces are the same idea as free surfaces, except for that's inside of material, such as things like grain boundaries. The thing is, the interfaces aren't going to match up perfectly. So a grain is a zone of single crystal separated by grain boundaries, often written as GB, at least for us. And this is when we have polycrystals. If I have large grains, so here's my material, I have one grain that goes that direction, a grain that goes that direction, and some grains that go this direction. And they're pretty large grains. If it's large grains, it means that we have a small number of actual grain boundaries. I'm going to draw these grain boundaries in red. My grain boundaries would be here and here, and those would be my defects. Those are my surfaces, even though they're inside a material. Large grains, small number of grain boundaries per unit area, and there's it means that it's coarse grain or large grain diameter. And what this does is it makes it a ductile material. Again, we'll talk about that when we get into mechanical properties, but really it just means that it's not brittle. If I have a small grains, I'm not going to even draw these. I can have these small grains. Each one of these is having its own grain direction, similar to these larger ones, but let's say that this one goes that direction, and they're all not quite lining up. Lots and lots of interfaces in here. So if we have small grains, we have a large number of grain boundaries per unit area, or in other words, we have a lot of interfaces in here. We say that it is a fine grain structure, or that it has small grain diameters, and this makes the material very high strength and hard. Grain boundaries can be seen sometimes. To do this, we can polish the surface of our material. We can acid etch because the surface is going to be very, very highly reactive. We can put a little bit of acid on it. And depending on how the grain boundaries match up, it's going to dissolve each plane, each type of grain slightly differently at different rates, which means that we can see those grain boundaries. And some are really large and you can actually see them without a microscope. You can see in some galvanized materials, you can go out and maybe look at a chain link fence or something, or a flagpole or something, and you might see grain boundaries even just on the surface. They're large enough grains sometimes where we can see it. Sometimes they're super, super small where we would need a microscope. And sometimes, often, we can't see those grains ourselves at all, and we'd need to maybe etch it, or we would need to have some other method to take a look at those grain boundaries. The last thing I want to discuss is bulk defects. Bulk defects are our three-dimensional defects, and really they come in two forms. Either I have voids or vacancy clusters, big chunks of nothing inside my material, or going kind of back to Democritus, we want to talk about how he was saying there was voids in being. We could say that I could have this big chunk in my material of some type of being. It is a chunk of some material that really shouldn't be there, at least not as the bulk material goes. We could manage this. We could put in some type of filler, such as rocks or shells in concrete, or it could be uncontrolled, such as slag in material. There are some links here that I'm going to try to remember to put in the description of the video, where it talks about the Titanic and why the Titanic sank. They've recovered some rivets from the Titanic, and they have done some testing on them, and they have found that, let me go ahead and just jump into one of these real quick. They've done some tests on them, and they found that the way that they break, I think I wanted to jump into the other one. There were bulk defects in them. And so they measured it and they found where bulk defects were inside of the material. Now what the bulk defects were on this is to make the steel, you want to make sure that you heat it up long enough to make sure all the slag floats to the top, so you can remove all the slag, all the stuff that you don't want, such as when you take iron ore, there's some sand and there's other things mixed in with it. You want to make sure that that comes off so that you have a more pure material. And if you don't allow that slag to come out, that sand basically turns into a glassy, brittle material. And for a rivet, that's a bad thing. That means the rivet, the thing that's supposed to be holding the hull together, the boat together, isn't going to be very tough. It's going to be able to shatter. And so that's something that we, again, might get back to later. We can talk about it in class a little bit. But it is an example of a possible reason why the Titanic sank, and getting back to what a bulk defect is. I do have this one picture here of a real-world example. I got sidetracked once when I went to the mall. I was walking, and all of a sudden I just stopped dead in my tracks, pull out my phone, and take a picture of the ground here. And the reason for it is it's a perfect example of an interface. So this goes back to our two-dimensional structures. Or not our two-dimensional, our surfaces, our two-dimensional defects, where there's some tile that goes in one direction, and if you just look at the right-hand side, it's a perfect crystal structure, and there's some tile on the left-hand side, and again, looking at that by itself, it's a perfect crystal structure, just a bunch of squares. But where they meet up, they don't meet up perfectly. And so we can definitely see where we might have unmet bonds, which gives us our high energy. And so I don't have bonds that match up so that each lattice site has the proper number of bonds and the right angles and all that. It really allows for a spot of high energy in the material. And I also like talking about this because it can show you that looking at the real world, looking at all different types of things, it can really help us understand science, materials, physics, chemistry, and engineering, just kind of by being observant in the world around us.